Hi, this is the 36th edition of Physics Night. This is Sir CJ, and in this session, we are going to have the following parts. The first one being under the gather information, which is a discussion about the transformation of energy, but this time, transformation of energy that happens among objects that were thrown. Okay, and it's somewhat similar to our discussions when we were still discussing projectile motion. And then the second part naman is still under gather information. It's a problem solving kind of discussion. We will be dealing with the sample problem, and then later on, you're gonna be dealing with your own independent problem. This session, this 36th session, is based on the 7E based self learning module in Science 9, which I wrote particularly from Unit 4. You'll find this in Unit 4, book number 22, pages 15 to 17. The learning competency in focus for this session is performing activities to demonstrate conservation of mechanical energy. So we're quite being thorough here. We're not just discussing about things that were rolling. We're also discussing things that are simply falling or were thrown in the air. All right. So the first part of this session is discussion. The energy conservation mechanism in the sliding down of a cart in the roller coaster track has the same mechanism as throwing a ball. So observe the patterns in this illustration and analyze its components. So first, the potential energy is increasing, whereas the kinetic energy is decreasing. And then it will reach its highest point where its potential energy is at maximum, whereas its kinetic energy is at zero, made obvious by this sudden stopping of it mid-air. And then, as it falls, the potential energy is decreasing, and because as it falls down, it's not actually gaining any positive acceleration in there. It's gaining negative acceleration due to the fact that it's traveling along the negative y-axis. And then its kinetic energy demand is actually increasing. All right. The overall kinetic energy of the ball in its highest point is zero because again, it is bagas. It stopped mid-air. It will move downwards due to the pull of gravity. Its path is along the negative y-axis, decreasing its gravitational potential energy. But in the process, it's actually increasing its kinetic energy, its movement. It's becoming faster. Right, so keep that in mind in talking about or in discussing the following sample problem on energy conservation, but this time, energy conservation that happens among thrown objects. So, in one of their team events, Jennifer threw a baseball ball straight upward with an initial velocity of 17 meters per second. Now, the question is how high, or in terms of height, vertically, will the ball go? So, the given factors are the following. The initial velocity was 17 meters per second. The final velocity will be 0 because it is the velocity of the object at its highest point. That's what we'll be using because the question is actually asking for the distance when it reached that particular point. Now, the next given, which is a constant, is 9.8 meters per second squared because again, we're dealing with gravity here. So we have to put acceleration due to gravity. The missing factor is the final height or the height of the object at its highest peak. Now, for the solution, we use the following formula, the whole one, the one that is like in the previous problems. But this time, since the mass was not given, we can just cancel them out from the formula. Okay, and we along with the cancellation of mass in most cases in this formula, if it's sitting beside the acceleration due to gravity, we can also cancel it out. Okay, so we'll be left with the following lang. It's gonna be VI squared, kasi wala na siyang mass, multiplied by 2G is equal to HF. Alright. Now, the formula is gonna be used in substituting the factors. So you may now take your time in putting the values for the factors here. But remember that we are looking for HF, so you keep that blank. Are you done? All right. So for the missing factors, we plot them like this: 17 meters per second. It's gonna be squared later on. Divided by 2 times 9.8 meters per second squared, it's going to be equal to the final height. Okay, so we carry out the operations. What will you get? You square it, okay, and then you multiply. Do you get? Okay. Do you get the following? So squaring it, it's gonna give you 289 meters squared second squared, and then multiplying them will be giving you 19.6 meters per second squared. Notice how the second squared is just gonna cancel each other out entirely, but meter squared over meter is just gonna cancel one of these meters, where you're gonna be left with 1 meter, yeah, 1 unit for a meter over here. Now when you divide 289 by 19.6, what you get is 14.7 meters, and that is the maximum height reached by the ball. Right, it's quite easy, isn't it? It's easier. Now it's your turn. Go over this problem and, of course, solve for the missing factor. Following Jennifer's attempt to throw the ball straight upwards, Hermes threw it harder. Actually, it's supposed to be through like THREW. Okay, I'm so sorry for that oversight. Hermes threw it harder straight upwards with an initial velocity of 20 meters per second. So kanina 17 lang, but this time it's 20. Now, how far do you think will the ball go? You may now begin answering this question. Are you through? All right. Your answer is supposed to be 20.41 meters. Okay, so it's obviously quite higher. Is it quite higher? Yes, it's a lot higher actually, compared to the previous case with Jennifer, who only was capable of throwing it with an initial velocity of um, it's only 17 meters per second. This time it's 20. That's why it also went higher. All right, this session is actually quite fast, isn't it? Now, in processing that information, there is undeniably a strong connection between energy transformation and energy conservation. So, in numerous inventions, technological products, and processes alike have been made through the years thanks to the countless men and women of science in each generation. There is something significant about the discovery of or the proposal of the law of conservation of energy, though. This law states that energy is neither created nor destroyed. It has been the baseline law of most sciences that were born from physics. But what is that controversy that surrounds it? You're gonna be discovering more about that in the next video lessons. But for the meantime, let's wrap this up. In this session, the 36th session of Physics 9, you are capable of discussing energy transformation that happens among thrown objects. You are capable of solving a guided sample problem along with me, second part. And then the last part naman, you did it entirely by yourself in an independent problem solving activity. Remember that everything in this session are found in the 7E based self-learning module in Science 9, which I wrote, particularly in unit number 4, book number 22, pages 15 to 17. And we are still in the process of mastering the following learning competency, which is performing activities to demonstrate conservation of mechanical energy. This is our CJ, and I am having a great day. I hope that you, too, are having a great day so far.